welcome to Physics 100. I'm Professor Curtis, your instructor for this course. This is the lecture for Chapter 27, Color. Let's get started. First of all, we need to understand that what we interpret as color is simply differences in the wavelength or the frequency of visible light. So we talked in the last lecture about the electromagnetic spectrum, and there's a rough range of wavelengths that correspond to different colors. And remember, the convention that we're going to use is when we're talking about visible light, we're going to talk about wavelengths, and for everything else we'll talk about frequencies. So we have conventions for the different categories of color that we see: red, orange, yellow, green, blue, indigo, and violet. Red has the highest wavelength, which means it has the lowest frequency and hence the lowest energy. Violet, on the other end of the visible spectrum, has the shortest wavelength, therefore the highest frequency and the highest energy. White is the combination of all colors, and black is the absence of all color, which is actually kind of interesting. It's like, when you think about what these colors have represented throughout history, white, typically a color that represents purity. And so if you think about that, purity comes from taking everything in and being inclusive, whereas black, the absence of all colors, so we think about black as being evil, and, the absence of all color, we've taken everything out. So white is where we take all the good in. We've combined all the good from everybody, and black is where we take all the good out. This is kind of interesting how the physical world kind of reflects that. So we have what we call selective reflection. Essentially, objects that are a certain color are basically absorbing every light wavelength except the one that corresponds to the color we perceive. So if an object is blue, it's because it's absorbing all light but blue light, and it reflects the blue light. That's why we see the blue light, because that's what it reflects. Everything else is absorbed. So, of course, if white is the combination of all colors, that means white objects are absorbing light of no color. They're reflecting everything back. It's that combination of what's reflected back, combination of all the colors, makes white. Of course, black is the opposite. If something's black, it's because it's taking everything in. It doesn't reflect anything back. And again, when you think about something that's inherently good, okay, people that are inherently good, they're always giving. They're always giving to other people, and they're always sharing. And so the goodness that comes to them, they share back out into the world around them. They're reflecting that back out. But people that are just downright evil, they're not giving anything to other people. They're always taking. They're always taking. And so they're not reflecting anything back. Again, another nice parallel there between what we see with people and what we see with the actual physical world. Anyway, this is an effect that we call selective reflection. There's also an effect called selective transmission, which kind of works the same way. So we have objects that are transparent, but they appear to be a certain color because they're absorbing everyone except the one for the wavelength of the color we're perceiving. So stained glass windows get their color from this effect. Okay, so each portion of the stained glass window has a different color, and that means that, the one that's matching is what's actually being transmitted through. It's selective transmission. So blue glass appears blue because it absorbs everything but blue light, which it transmits. And that's how we see the blue. Of course, clear objects are absorbing any light. They're transmitting everything out. And this is an effect that we call selective transmission. So now we're going to watch a nice little video here about color. It provides a good overview of what we discussed so far, and also some of what's coming up just around the corner. So there's a number of colors that we see here in the video, and let's see if I can get this to work. All right, here we are. Let's get started with this.
hillsides where once there were hickory and chestnut.
Okay, so like I said, a really good overview of what we've talked about so far with color. And it's also a slight preview as to some of the things that we're going to get into here in a moment. So with that said, let's go ahead and move ahead here. I can just to go forward. There we go. All right, so now let's talk about different types of colors here. So we're talking about light. We have what are known as additive primary colors. So these are going to be red, green, and blue. And you can see from what we call here the color wheel over here on the side, the color wheel is showing us the different primary colors there on the outside edge. So we've got red, green, and blue. These are the additive primary colors. So we've got red, green, and blue. And we call these the additive primary colors because we can get any other color in the spectrum just by adding the right combination of the additive primary colors together. So notice when we get all three to combine to each other, it produces white. So that center portion of the color wheel where you've got the red light, the blue light, and the green light showing that they overlap each other. Combine them all together, that gives us white light. And this is what many monitors and TV sets and projectors are using to create color images, additive primary colors. Now, in addition to the primary colors, we have what are called complementary colors. So we're just basically taking two of the additive primary colors and putting them together. So magenta comes by adding red and blue together. Or if we take red and green, put them together, that gives us yellow. Or if we get cyan, that's the combination of blue and green. So these are what we know as the complementary colors. And the waveform for complementary color light is just the addition. So that means we're superimposing the waveforms of the light for the two additive primary colors that make it up. So when you add a complementary color with its opposite color, you get white light because, the opposite color for the complementary color is going to be the one of the three primary colors that you didn't put in to make the complementary color. And so that's where you're going to get white light because now you've got everything put in. So opposite colors are what form when, like I said before, the opposite colors combine. So you've got a complementary color and its opposite color, the primary color you didn't leave in. Those are opposite colors. And that's where the color wheel comes in handy because you can see everything. Just look at the opposite side of the color wheel. So, magenta is there on the color wheel towards the upper left. Opposite on the other side is green. So if you put those two together, you get white. Yellow is on one side, blue is on the opposite side of the color wheel. Those are opposite colors, so they combine to give you white. Cyan and red, opposite colors, again combine to give you white. Note that one of those colors in the mix is a primary color, and the other is a complementary color formed by the other two primary colors. So that's why you're getting white light when you put opposite colors together, because you're basically taking all of the primary additive colors and putting them together. So, looking at the color collage there in your workbook, go ahead and stop the video and answer these questions. What color do you get when you combine red and green light? What color do you get when you remove blue light from white light? What color is the opposite of red? What complementary colors are combinations of blue? And what color do you get when you combine magenta, cyan, and yellow? Go ahead, stop the video here, work out these questions in your workbook, and then come back and we'll see how well you did. Okay, let's see how well you did with this. So, First question, what color do you get when you combine red and green light? And the answer is yellow. So if I look here at my color wheel, so I got red here, I got green here, so I put them both together, and what I get here is the combination of them. That's going to be yellow. What color do you get when you remove blue light from white light? So if I take the white light here and I remove the blue light, that's going to put me over here toward this side of the color wheel, and that's going to give me, again, yellow. What color is the opposite of red? Well, I just look at my color wheel. Here's red. On the opposite side of the color wheel, here we have cyan. What complementary colors are combinations of blue? Okay, well, here's the blue side. So the complementary colors are going to be the ones in the middle. So it's going to be these two colors here. That's going to be magenta and cyan. Then the last question, what color do you get when you combine magenta, cyan, and yellow? So here I've got, on my color wheel, I've got magenta, I've got cyan, I've got yellow. So I put those three together, and I get the color there in the middle, which is white. Now we can flip this around and talk about subtractive primary colors. And the reason why we do that is because, what we've talked about with the additive colors, it works really well for light. But when you're looking at pigments, like in paint, then it doesn't quite work out the same way. So when you're talking about pigments in paint, you really need to flip this around and look at what we call subtractive primary colors. So the difference between the additive and subtractive primary colors is the same difference that we see between selective reflection and selective transmission. Okay? And so it's because of this reason that we use pigments and dyes to make different colors with subtractive primary colors, magenta, yellow, and cyan. So notice how everything got flipped on my color wheel here. Okay? So what was a complementary color before is now a primary color, and what was a primary color before is now a complementary color. And black is there in the middle, the combination of everything, and we'll often add that when we're printing something in order to sharpen the image out. And so if you notice, color printing devices, like if you've ever had to replace the inkjet cartridges in a modern day printer today, so the inkjet printers use subtractive primary colors to create images. And this is why you've got those three colors there, magenta, yellow, and cyan. Those three colors there, you've got cartridges for each of those colors, and that's why you have them there in your inkjet printer, because they're using subtractive primary colors. When you're printing something or painting something, you got to use subtractive primary colors. The additive primary colors are what you use when you're talking about light projected images. But when you're talking about something that's printed onto a medium like paper or whatever, then you're going to have to be using subtractive primary colors. What we've learned today helps us to understand the colors that we see in the atmosphere. Okay, now those colors are mostly due to the scattering of individual light rays among the atmospheric particles. So you've got all kinds of things up there in the sky. You've got molecules of nitrogen, molecules of oxygen, molecules of carbon dioxide. You've got water vapor that's forming the clouds. And so all this stuff that's there in the atmosphere, all these particles are being scattered around, and the light rays that are coming in from the sun get scattered by all of these particles that are all over in the atmosphere. Well, why is it that we see the sky is blue? Well, that's because the nitrogen and oxygen molecules in the atmosphere are scattering violet light the most. And then they scatter blue light a little less, green light a little less, yellow light a little less, orange light a little less, red light the least. Our eyes are not really sensitive to picking up violet light, and so we see the next color that's scattered the most, which is the blue. Now, as I said before, clouds are just different size it's just water vapor, so you've got different sizes of droplets there in the clouds. And of course, different sizes of droplets are going to scatter the light differently. Different wavelengths of light are going to come out of different sized droplets. So since you've got droplets of all sizes there in the clouds, you get wavelengths of all the light that are scattered, and that's why the clouds look white, because again, white is the color we get when we combine all the other colors together. What we've learned also explains the colors that we see when the sun is rising and when the sun is setting. So the colors that are predominant here are red, orange, and yellow. Notice we're at that one end of the visible spectrum. These are light rays that are scattered the least. Well, why would we see these colors more predominantly when the sun is rising and setting? Well, you're looking at the position of the Earth with respect to the sun. So when the sun is there on the horizon, it has a longer path for the light to travel. And with a longer path, there's more time for the wavelengths that get scattered to be more scattered. So the ones that are scattered the most towards the violet end of the spectrum, they get scattered even more to where we don't really pick them up as much. And the ones that are scattered the least on the red end of the spectrum, they're not as scattered, and so they get picked up. And this is what lets those wavelengths of light to make it through. And that's why we see the colors at sunrise and sunset predominate as red, orange, and yellow. This also explains why waves in the ocean appear to be a greenish blue color, because water is going to absorb red light more than wavelengths of other light. So it absorbs that red light the most, so that means it's going to absorb violet light the least. But again, okay, our eyes aren't really, adapt to picking up that violet light as much. And so you take white light and you take the red out that is being absorbed by the water, then what you get, because we can't pick up the violet, is a greenish blue color that's the opposite of red. So remember the color wheel, we had the opposite of red was cyan. That's that kind of greenish blue color. And that's what we get out. That's why the ocean waves look that color. And that brings us to the end of this lecture. Hope you found it helpful. Thanks for watching, and we will see you in the next video.